Welcome all. Now we are discussing lemma 5.4. Let x be a normed space and y be a subspace of x. And first part is, for every x element of x, y element of y and k element of k, we have norm of the element kx plus y is greater than or equal to modulus of k into distance of x with y. And the second part is, let capital Y be finite dimensional, then y is complete. Okay, that is every finite dimensional subspace of a normal space is complete. In particular, it is closed in X, and then let y1, y2, etc. ym be a basis for y and xn be a sequence in y. If xn converges to x, if and only if the k in j's converges to kj as n tends to infinity for every j equal to 1 to m. Also, the sequence xn is bounded if and only if the sequence of k and j is bounded for each j equal to 1 to etc. m. Okay, now we will discuss the proof of a part. Okay, if the scalar k is equal to 0, then norm of kx plus y is equal to norm of 0 into x plus y, that is equal to norm of y. Okay, and then modulus of k into distance of x with y is equal to 0. Thus we have 0 is less than or equal to norm y. This is clearly true. So when k equal to 0, the result is true. Okay. When k is not equal to 0, then norm of kx plus y is equal to norm of k into x plus y by k, and this is equal to modulus of k into norm of x plus y by k, and this is equal to modulus of k into norm of x minus y by k, and this is greater than or equal to mod k into infimum of set of all norm x minus y, where y is an element of y, that is modulus of k into, this is what, distance of x with capital Y. So we have this is happened since minus y by k is an element of y. Okay, and thus we have norm of kx plus y is greater than or equal to mod k into distance of x with capital Y for every scalar k. Now we will discuss the proof of part B. That is, first that y is finite dimensional. Let y be finite dimensional. Then we have to prove that y is complete first. Okay, that is every finite dimensional space is complete. So this is a very important result. We have to show this by using mathematical induction on the dimension of y. Okay, let dimension of y is equal to 1. Then let us name it as m. M is the dimension of y, and that is equal to 1. Then it has a basis. Then y has a basis. With a single element y, where y is not equal to 0 because basis contains non-zero elements only, and every element of y is in the form a scalar multiple of this basis element, where k is an element of k. Okay, now we have to show that y is complete when the dimension is equal to 1. So for that we have to choose a Cauchy sequence. Let xn be a Cauchy sequence in y. Then the form of each element in the sequence is some constant scalar multiple of y, where kn is an element of k. Okay, then norm xn minus some xp is equal to norm kny minus some kpy. This is equal to norm of kn minus kp into y. This is equal to modulus of kn minus kp into norm y. That is, modulus of kn minus kp into norm y is equal to norm xn minus xp, right? This means that sequence kn is a Cauchy sequence in k, since sequence xn is Cauchy. Okay, and we know that the space of scalars k is complete, and so sequence kn converges in k, since k is complete. Okay, let sequence kn converges to k, then our sequence xn converges to ky. Okay, this is clearly an element of y. So this means that every Cauchy sequence in y converges in y, and so y is complete when the dimension is equal to 1. Now let us suppose that every m-1 dimensional subspace of x is complete. Okay, now assume every m-1 dimensional subspace is complete. Okay, and let y be m dimensional now. Then it has a basis. Let y1, y2, etc. y be a basis for y. Then let z equal to span of the basis elements, not fully, from y2 only, y2, y3, etc. ym is m-1 dimensional subspace of y, and so of x, of course. Okay, then z is complete by our assumption. Okay, now we have to show that y is complete. Okay, for that let xn be a Cauchy sequence in y. Okay, then each xn is a linear combination of the basis elements y1, y2, etc. ym. Okay, that is some k1 y1 plus k2 y2 plus like something in the form. Okay, then this portion is clearly an element of set. Okay, so each xn can be represented in the form some kn into for this reason the suffix is n here, so we have to choose the suffix n here for y1, kn y1 plus an element of set named as zn. Okay, so each xn can be represented in the form some scalar multiple of y1 plus an element of zn. Okay, for some kn element of k and zn element of z. Then norm of xn minus xp is equal to norm of kn y1 plus zn minus kp y1 plus zp. Okay, and this is equal to norm of kn minus kp into y1 plus zn minus zp. Okay, this is greater than or equal to modulus of kn minus kp into distance of, this is an element y1 and this is an element of the subspace z. Okay, this is we have written this by the a part we have proved above. Okay, and as we know y1 is not an element of z, and so distance of y1 with z is clearly greater than 0 since z is closed by our assumption, that is every m-1 dimensional subspace is complete and in particular it is closed. Okay, അപ്പോൾ z closed ആയതുകൊണ്ട് distance of y1 with z is clearly greater than 0, and from this we get modulus of kn minus kp into distance of y1 with the z is less than or equal to norm xn minus xp. This means that sequence kn is a Cauchy sequence in K since xn is Cauchy, right? Therefore zn equal to xn minus kn y1 is Cauchy in Z, since sequence xn and sequence kn are Cauchy. Implies sequence zn converges in Z by our assumption, that is Z is complete and so every Cauchy sequence converges. Let Zn converges to Z in capital Z, and let sequence Kn converges to small k in capital K. Then xn equal to kn y1 plus zn converges to k y1 plus z in capital Y. This means that sequence xn converges in capital Y, and so capital Y is complete. In particular, capital Y is closed also. So we have proved that every finite dimensional subspace of a normal space is complete. Next we have to show that let xn is in the form kn1 y1 plus kn2 y2 plus etc plus knm ym, and x equal to in the form some k1 y1 plus k2 y2 plus etc plus km ym. Suppose that xn converges to x. Okay, suppose xn converges to x, then norm xn minus x is equal to norm kn1 y1 plus kn2 y2 plus etc plus knm ym minus k1 y1 plus k2 y2 plus etc plus km ym, and this is equal to norm of kn1 minus k1 of into y1 plus etc plus k nm minus km into ym. Okay, and let yj be the subspace spanned by yi's, where I equal to 1 to etc m and I is not equal to j. Okay, that is capital Y1 is the span of y2 y3 etc ym, and capital Y2 is the span of y1 y3 etc ym, and so on. Okay, so the particular element y1 is missing in the span of in the subspace y1, and y2 is missing in the subspace capital Y2, and so on. So clearly yj, small letter yj is not in capital Yj, and capital Yj is closed by our assumption, and so distance of small yj with capital Yj is clearly greater than 0. Okay, so from the relation we have reached, we get that norm xn minus x is equal to this quantity norm kn1 minus k1 y1 plus etc plus knm minus km into ym. This quantity is greater than or equal to modulus of kn1 minus k1 into distance of y1 with the, this is an element of capital Y1, and this is true for every index 1 to m. So we can write this as knj xj, distance of yj with the capital Yj. This is true for every j equal to 1 to etc m. Okay, and distance of yj with capital Yj is greater than 0, and this means that sequence knj this means that modulus of knj minus kj tends to 0 as n tends to infinity, since xn converges to x, implies knj converges to kj for every j equal to 1 to etc. m. Okay. Conversely, suppose that knj converges to kj for every j equal to 1 to etc. m. Then norm xn minus x is equal to norm kn1 minus k1 into y1 plus etc. plus knm minus km into ym. This is less than or equal to modulus of kn1 minus k1 into norm y1 plus etc. plus modulus of knm minus km into norm ym. And we have supposed that knj converges to kj for every j, and so this quantity converges to 0. So this converges to 0 as n tends to infinity. So we get the sequence xn converges to x as n tends to infinity. Finally, we have to prove that the case of boundedness also. Let sequence knj is bounded for every j equal to 1 to m. Then we have to prove that sequence xn is bounded also. Okay, let this sequence is bounded means modulus of knj is less than or equal to some alpha j for every j equal to 1 to m. Okay, then norm of xn is norm of what is xn? kn1 y1 plus kn2 y2 plus etc. plus knm ym. This is less than or equal to modulus of kn1 into norm y1 plus etc. plus modulus of knm into norm ym. And this is less than alpha 1 into norm y1 plus etc. plus alpha m into norm ym. Clearly this is a finite quantity and positive quantity. This means that sequence xn is bounded. Conversely, suppose that sequence xn is bounded. Okay, then we have to prove that each sequence knj is bounded. Then norm xn is equal to norm of kn1 y1 plus kn2 y2 plus etc. plus knm ym. This is greater than or equal to modulus of knj into distance of yj with the capital Yj, where capital Yj is the span of, as we defined above, span of y1, y2, etc., yj minus 1, yj plus 1, etc., ym. Okay, and so distance of yj with the capital Yj is clearly greater than 0, since yj is not an element of yj and yj is closed. Okay, so this means that since sequence xn is bounded, we get modulus of knj is less than or equal to norm xn divided by distance of yj with the capital Yj. This is a positive quantity and sequence xn is bounded, means that sequence knj is bounded for every j equal to 1 to etc. m. This is the proof of our theorem. Very lengthy proof. So read it once again and fix it carefully. Thank you.